Hello, welcome back to our hodgepodge chapter. The first part, the first video, it was a hodgepodge, but it was almost entirely review. This part will have more new material, so stuff we haven't actually had already. Okay, so we're going to begin talking about energy density, which is basically a way of just saying how much energy I have in a given volume of space. That's energy density. Remember, energy doesn't take up space, but it exists in space. There is energy here, and energy is doesn't doesn't necessarily have mass, so it's not necessarily made of taking up space, but it's there, right? It has that energy exists within a volume, and the energy density is basically the total energy divided by that volume. Now, for electromagnetic waves, it turns out that energy density is equal to 1/2 epsilon naught permittivity of electrical permittivity times the electric field strength squared plus 1/2 with mu naught, which is the magnetic permeability of free space, times the magnetic field strength squared. Now, this equation isn't so important. But what I do want you to know is that U, energy density, is equal to total energy per volume. And the next concept to understand is that the contribution to the total by the electric field and the magnetic field are equal. So 1/2 epsilon naught E squared equals 1/2 B squared over mu naught. And another thing to keep in mind, why is it 1/2? Well, the reason it's 1/2 is because this is not really E squared. It's E over the square root of 2 quantity squared, because we're using the root mean squared values, because this is being caused by an alternating current. So that's where the 1/2s are going in. So since these two, the contribution from the electric field and the magnetic field, are equal, I can make this relationship. And therefore, if I plug one in, so if I take the E, if I solve for E and plug it in, or I solve for B and plug it in, I can solve this equation knowing only one of the two. So this U, total energy over volume, equals epsilon naught E squared, because if everything else cancels out, or it equals 1 over mu naught B squared. Basically, because if these two are equal, then I can just substitute one in. So I would have 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared would be epsilon naught E squared. 1/2 plus 1/2 is 1. So mu is equal to epsilon naught E squared, or it is equal to 1 over mu naught B squared. This U and this U are mu, and this U are not the same. This is energy density, and this is magnetic permeability of free space. Okay? And these epsilon naughts and mu naughts are constants that we've talked about before, and they're actually part of one of Maxwell's equations, that the speed of light is equal to mu, or 1 over the square root of epsilon mu. If I use this relationship in addition to this relationship, I get one additional relationship, which tells us that the electric field strength is equal to the magnetic field strength times the speed of light. So let's summarize, because there's a lot packed into this slide. The actual energy is carried equally by the electric and the magnetic fields. So therefore, the contribution of one part, of the E part and the B part of this equation, are equal. Therefore, I can solve for energy density knowing only one, E or B. I don't need to know both. I only need to know one to know the total energy density. And furthermore, if I only know one, I know the other because of this special relationship. Once again, proving how important that value of C is to the universe. So let's look at an example that I would make use of this relationship. And this is where I was telling you why it was 1/2, because of the root mean squared. So let's look at an example. Sunlight enters the top of the Earth's atmosphere with an electric field whose E root mean squared is 720 newtons per coulomb. Find the average total energy density and the root mean squared value of the sun's magnetic field. Well, I can relate mu to E by the equation mu is equal to epsilon naught E squared. Epsilon naught is a constant, which happens to be 8.85 times 10 to the negative 12th. That constant times 720 squared will give me 4.6 times 10 to the negative 6th joules per meter cubed. Joule is energy, meter cubed is volume, energy per unit volume, energy density. Now, since I know E, I can also solve for B. B is equal to E divided by C. 720 newtons per coulomb divided by 3 times 10 to the 8th meters per second equals 2.4 times 10 to the negative 6th Tesla. So all of these values are related. That's one of the things about electromagnetism. So many of the equations relate to each other. And when you know one thing, it's super easy to solve for many others. Now let's move on now to, so this was energy density. Let's move on now to intensity of an electromagnetic wave. So we know from before that energy is power times time. Well, power can be defined as intensity times the area through which that intensity moves. And that intensity, therefore, if I set these two equal to each other, the time cancels and intensity equals power per unit area. So that's one thing to keep in mind. Intensity, by definition, is power per unit area. And that makes sense. More intense, more power in the amount of space that I'm taking up. Now, if power is total energy per unit time, and I replace that back in there, and I then replace total energy with energy density times the speed of light times time times the area through which it travels, that's total energy, everything cancels out, and I'm left with another relationship that relates to intensity of a wave. And once again, the speed of light comes into play. Intensity of a wave is equal to the speed of light times, as we know before, the U, which is this energy density. Energy density times the speed of light is equal to intensity. So you should know that energy is equal to intensity times area times time. You should know this equation. You should know that intensity, therefore, is power over area. That's the same as this equation, just solved. So you don't really need to know this, but you should know that S is equal to Cu. That's what you need for the bottom here. Now let's look at an example from the review guide for this. So we already did the sunlight example up here. That was in the notes, but let's look at this self-test example just to show you how it works. Electromagnetic radiation has an intensity of 1390 watts per meter squared. When it reaches an area in space of width 25 meters and height 45 meters, how much energy is expended in 3,600 seconds? Now, if I gave you a value in minutes or hours, you'd have to convert it to seconds. If I gave you a volume in something other than meters, you would need to convert it to meters. Because intensity is watts per area, and it's not volume, it's not surface area of a sphere, it's the flat surface area that it's moving through. But it could be surface area of a sphere, but usually you're talking about like what's the intensity moving through this square per unit, and so it's like joules per second, watts per unit area. So going back to my equation, E is equal to SAT. I gave you S. I gave you a way to calculate the area because I gave you length and width, or height and width. I gave you time, so it's 1390 times 25 times 2045 times 3600. Intensity times surface area times time equals the energy. So those are the kind of questions that you would want to be able to answer. So now let's move on to the Doppler effect. Now, I just want you to understand that the Doppler effect is much more complicated mathematically in electromagnetic radiation, even though this equation is going to make it look like that it's not. Now, one way that the Doppler effect for electromagnetic radiation is easier is in the way that we were looking at it without actually realizing we were looking at it that way for sound. With sound, we had to take into account the movement of the observer, and we had to take into account the movement of the source, and we took them into account separately from each other. The reason for that is because we were measuring both of their velocities relative to the Earth, because the air that the sound is moving through is basically moving with the Earth. So the medium becomes much more important, whereas electromagnetic radiation doesn't care about the medium. It cares about this wave is moving relative to this wave. So only the movement of the waves relative, the source and the observer, only their movement relative to each other matters, not their movement relative to some other object like the Earth or the air. So only one relative velocity matters in most cases, and that's v-REL, v relativity. Now, this particular equation that I'm giving you is just one of many for relative movement of electromagnetic radiation, but it will serve like for certain examples that I'll give you. And it's the only one that our book uses because it only applies, but it's a very good equation when the relative velocity is much less than the speed of light. So it's really good for when you want to mix light with slow objects like us. And that's a pretty common thing that you want to do. And in this case, you only have one term. You only have a numerator. You don't have like a big denominator factor, and there's no squared. Because remember, it was 1 plus or minus v squared over c squared in the sound Doppler effect equation. So our equation here is frequency of the observer equals frequency of the source times 1 plus or minus relative velocity divided by the speed of light. And that plus or minus here is determined whether or not they are moving towards each other, away from each other, or in the same direction. And then if you do this enough, you start to walk like an Egyptian. And so let me give you an example of how this works. Radar gun of a police car emits an electromagnetic wave with a frequency of 8 times 10 to the 9th hertz. Now we can use it here because that radar wave is going to be moving much faster than any car could ever hope to move. Now these two vehicles are approaching essentially head-on. The wave from the gun reflects from the speeding car and returns to the police car, where onboard equipment measures its frequency to be greater than the emitted wave by 2100 hertz. Find the speed of the car with respect to the highway. The police car is parked. Now this is actually a two-part question. You're going to use the Doppler effect twice because the radar, I'm not asking you what the radar is, how the radar is being picked up by the car. I'm asking you how the reflected radar is being picked up by the police car. So let's look at this. First of all, the frequency of the source is the source leaving the police car. Frequency observed is what the red car is picking up on. And since they're moving towards each other, we're going to use this plus, okay? Basically, their velocities are being added together. So I add the relative velocity divided by the speed of light. Now that gives me a new frequency. This is the FO is the frequency of the radar being reflected off of the car, which becomes a new source. So that FO goes over here. And now you still have the same V relative over C factor, but the police car is going to be the observer of the wave that was reflected off of the car. So the first observer is the car, the second observer is the police car. So I first have to figure out how the frequency changes between the cop car and the red car. And then that new frequency will bounce off the red car and be changed based upon their movement once again. So it's kind of like the effect is being compounded because of the fact that it's reflecting. Now, using some fancy math, which you can kind of skip through because I'm simplifying, but it turns out that in this case, so f naught prime minus f of s is equal to f naught minus f of s plus f naught v relative over c minus fs v relative over c. Because of the fact that v relative is much less than c, I can simplify this to being minus f of s minus f of s v relative over c. I don't know how I want to explain to you how it gets simplified. Do I want to go into all that math? I just want you to understand, I guess in the end, that in questions like this, there is a relationship between the final observed frequency and the initial frequency. And in this case, so I'm going to skip a lot of this math step. You can look through it and work on it on your own if you really want to understand it. There's more descriptions in the book. But for time here, I'm just going to go to the point where the relative velocity between those two vehicles, all right, since only one of the vehicles is moving, that makes it a little easier, but it doesn't, since only one of the vehicles is moving, our relative velocity will be entirely due to the red vehicle at this point. So that relative velocity, which is the same thing as the red car's velocity, will equal to the frequency that the cop car observed minus the frequency of the source. And that's what the radar detector tells you, that difference. And that difference is 2100 hertz. And then 2 times the frequency of the source. The source frequency was 8 times 10 to the 8th hertz. And then I multiply that by the speed of light, 3 times 10 to the 8th, and I find that it's going 39 meters per second, which means it's speeding because about 30 meters per second is 33 meters per second is a highway speed. So he's going a little too fast. So when you have relativistic Doppler effects or Doppler effects with the electromagnetic radiation, it is a simpler equation. That's what I want you to understand. And in this particular case, so if you were given an example where you needed to understand how cop cars can determine what speed you're going, which is a relative velocity, if the cop car is going a certain speed, all I need to do is subtract or add the speed of the cop car to the relative velocity to know what speed you're going. If we're both going in the same direction, I add my speed to the relative speed, so then I know how fast you're going. If that makes sense. Like if we're both going, if the cop is following behind you and I get that your relative speed is say 6 meters per second using this equation here, that would tell me that you're going 6 meters per second faster than me. And if I'm going 30 meters per second, then you're going 36 meters per second. So in any situation like this with the cop and a radar car, this equation will work to give me the difference in our velocities. And then I just add my velocity on to figure out what your velocity actually is. Another example where this works and where this is useful, and here we'll go to the review guide. So I'm going to resize this a little bit so I can get all of this in there. Let's say that we have an astronomer and he observes an electromagnetic waves emitted by oxygen atoms in a distant galaxy. And those oxygen atoms have a frequency of 5.91 times 10 to the 14th hertz. That becomes the observed frequency. That's the frequency that I perceive those atoms to be given off. In the laboratory on Earth, oxygen atoms emit waves that have a frequency of 5.841 times 10 to the 14th hertz. That, even though that's what I'm observing on Earth, that is also what the source would be because all oxygen atoms, I assume, in the universe are the same. So that 5.841 times 10 to the 14th hertz would be the source frequency. So I know what it should be, and I know what I'm actually reading. And what I'm actually reading is 5.91, but it should be 5.841. times 10 to the 14th. I can use that difference in frequency to determine the relative velocity of the galaxy with respect to me. So is that galaxy moving away from me or towards me, and how fast? Well, I have my Doppler effect equation. Frequency observed equals frequency of the source times 1 plus or minus v relative c. And I'm going to try and actually make this bigger, and I'll just move it around. Okay, so I have my original equation. First thing I do is I divide both sides by frequency of the source. I can then subtract 1 from both sides. I can then multiply both sides by the speed of light. And I now see an equation very similar to what I was seeing up here, where I have a ratio of frequencies times the speed of light will equal my relative velocity. So here I have the speed of light times the frequency observed divided by the frequency of the source, that quantity minus 1, will equal to the relative velocity. Now when I do this, I actually did this and had the value, but apparently didn't put it into here. So when you put those values in, you'll know what the relative velocity is. Now the plus or minus you can actually get conceptually here. Since the frequency is increasing, they must be moving towards each other. Because if they're moving towards, if frequency is increasing, wavelength must be decreasing, which means if they must be moving towards me because the wavelengths are being smushed. So I know that that frequency is increasing, that relative velocity will be towards me. That's why the whole like plus or minus relative velocity in this question, it doesn't really matter whether if it was negative, then we would be going away from each other, but clearly we're going to be going towards each other here. Now, if you are coming towards each other, we actually call that a blue shift because the wavelength will be getting smaller. Since the frequency is getting bigger, the wavelength is getting smaller, and that's a blue shift. Okay, let me shrink this back down now. Whoops. To regular size. So we've almost done all of the review guide. There's only a little bit left, some polarization stuff, and then one more self-test question. You can stop this video and start it back over, but I'm just going to try and work through and finish the whole thing in 2 videos because you can always pause and restart start them. But this would be a good point to pause, although you might have paused before the Doppler effect part. Nope. I take that back. I'm going to stop now. I'll finish up the polarization in the next video because why is it not all on the screen? Because partly part of it's being cut off here, but partly because I'm going to do a little bit of some summarization when it's all over with. So I'll start the next video, will probably be 10 minutes long.